Next presentation is on validation framework for module lattice-based post-quantum digital signature scheme by Abey, Jacob and others.
Today, basically we are from crypto module validation and testing lab. So we are where we do algorithm and module validation as per ISO 19790 standard. So this lab is set up at CDAC KP. Okay, so today I'll be starting with introduction, overview of MLDSA and parameter set for MLDSA algorithm, auxiliary functions which are used for MLDSA algorithm, MLDSA key generation, signature verification, and test procedure and validation results. So this will be our flow. So when we look at the overview of MLDSA, MLDSA is optimized SHOR-like lattice-based signature scheme. It is standardized by NIST in FIPS 204 called MLDSA, that is Module Lattice-based Digital Signature Algorithm. This relies on the hard lattice problems, module learning with error problem, and module short integer solution. So MLDSA standard, it has three parameter set. One is MLDSA 44, MLDSA 65, and MLDSA 84. So this research, it contributes to the validation procedures and systematic test vector generation with intermediate parameter verification to identify precise sources of implementation errors. So this is the parameter set for MLDSA algorithm. It includes modulus Q, ZQ, and matrix dimensions K, L, eta. For MLDSA 44, MLDSA 65, and MLDSA 87, it varies. So, and claim security strength for MLDSA 44 is category 2, and for MLDSA 65, it is category 3, and MLDSA 87, it is category 5. So, and here public key, private key bytes and seed and signature size are shown here. And auxiliary functions which are used in MLDSA signature are some of them we have listed here, like SHA-128, 256, SHA-3, 256, 512, which is used for expanding seeds, creating challenges, fixed length cryptographic digest, and entity, that is number theoretic transform, which is used for point-wise multiplication operations, encoding and decoding, which translates MLDSA public private keys into byte strings and vice versa. And expand A, which generates K bar L public matrix, expand matrix, expand mask, which produces masking vectors using seed, and hints are created during signing, and which is used for verification. So this is the flow of MLDSA key generation algorithm. So here we take a seed which is hashed to produce the public seed row, and private seed row dash, and signing seed K. And this is expanded into the polynomial vector matrix A cap, and secret test vectors S1, S2 are generated, and finally T is equal to S1 into S1 plus S2 is generated, and which is again split into the lower bits T0 and T1. This T1 is used for public key generation, that is PK, and hash of PK 64 byte is TR is generated, which is used for the private key. So encoding of the private key is done using row K, TR, secret vectors like S1, S2, and T0, which is the generated private key is generated through this. So this using seed, which private key and public key is generated, it is given as input for the MLDSA signing algorithm. So here input is SK, M dash is the random message, and RND. In MLDSA signing, there are two types of RND. One is we use two types of RND. One is hedged and the other one is the deterministic. So in hedged R&D, we use the random vectors. Random bits are generated, but in non-deterministic, 32 bytes of 0 is taken. And this private key, it is we extract all the parameters like row, k, s1, s2, t0, everything. And a cap is generated using row from sk. And this one message is mu message is generated by hashing tr and random message m dash, which is of 64 bytes. And the row prime is generated using hash of k rnd and message mu, which is of 64 byte. After this, the core of MLDSA signing is creating commitment, challenge, and a response. So here, commitment is created, challenge is created, and a response is created. So commitment is this W. This is a loop actually. So. So this is a rejection sampling loop where W1 is generated. Uh, then C hash is generated. This is the commitment challenge which is generated, and Z is the response. And using this hint polynomial is generated, where here we validate whether hint is properly generated. Some validation checks are done. If the hint is not properly generated, again the loop is repeated. Using and again new z y values are used, and signature is valid signature is generated. This loop repeats till the valid signature is generated. If the valid signature is generated, then encoding of the message z mod plus or minus q and h is done, and signature is given. And for ML DSA signature verification, here we give the private key message and signature as input. We from the private key we extract row T1, and from signature we extract C has Z and H. And here we validate whether the hint encoding is properly generated. If it is not generated, it is rejected as invalid. And a cap in entity form using row is generated. Message is again generated. And here there is a loop happening here for commitment, challenge, and response. So here the loop happens, and hint is used. Here we generate the hint, and we verify whether the output is valid. If all output is valid, if the output is valid, we say the signature is valid. If it is invalid, then the signature is not valid. So the validation test implementation will be continued by my colleague.
As algorithm FIPS 204 have like three for implementation criteria, there are three modules: key generation, signature generation, and signature verification. For key generation module, we have taken a 32 bytes of random seed, which given to the ML key generation, and they generate public key and private key. So in the request file, it is taken as a seed value, and for response file, it is PK and SK, public key and private key. For signature generation, we have a two scenario where either random value is taken as a deterministic or hedge version. So in both cases, we have taking private key and message. The private key which is generated from the key generation module, we are taking here. So in the response file, it is generating private key message and optionally R&D, and then with the signature value. For signature verification, we are taking public key, message, and signature, and the public key is generated from the key generation module itself. So, and then the output is either signature is valid or invalid. So this is the This is the output which is generated from the cryptographic algorithmic module. So here we can say MLDSA 44 signature verification. For each test record, it is a different, each record is a different test vector. So here PK, public key, message and signature is given. Private key is given for the completion purpose. And PK SK is generated from the key generation module. And here output is tell as a signature verification passed or signature verification failed. These are the references.
So these are the references. Thank you. Any questions?
Hello team, good evening. It's a good work I see in the PQC area, but just give me an abstract of what exactly is the challenge that you are posing to the quantum computers for it to be challenged to be not breakable. In the sense, say for example, we have an RSA or ECC, any of the existing algorithms, right? Encryption algorithms. So there is a weak point. Right? If you take RSA, then it's probably factorizing of the prime numbers, which is being challenged by the quantum numbers because of the speed and the ability of it. Now, what is the key thing in your PQC that is really going to challenge the quantum computers?
This challenge we generate in the signature generation time we generate, and while the signature verification time we generate the approximate challenge. So when we try to check the validity, that whatever the challenge we generated in the signature generation has to match with the verification. That is how we are validating.
So it's just matter of having a challenge and
yes. It should be almost all approximately same.
Okay.
So what is the computational challenge what sir asked? What is the challenge in terms of computation here? Can you?
Sir, let's. Sir, if you see, like in the signing, there is just rejection loop is there. So in generating the custom test vector, let's say 100 test vectors should be generated. 50 should be valid and 50 should be invalid. So we have to fix the how much loop should be there. So that way the computation for the custom text generation is like in paper also it is there, like 2.66 is the average we are taking for the generating the whole custom test vector.
Thank you.
Thank you.